all here for this third session out of the 4. Please let me know if there are any issues. If you can't see me presenting, can't tell if I am. Good to go. Okay, cool. Yeah, so well done for constantly keeping up the energy and coming back. I know not all these sessions are particularly easy. Last session was particularly hard, and this session is not as hard, but some way in that direction. Apologies for not getting the recording of the last session out too quickly. It just went up a couple of hours ago. There were, unfortunately, someone was traveling and didn't have internet, and okay, each one can't see the presentation. Yeah, that is it does say, nope, I'm no longer presenting. Hold on. Did I drop? Change audio output. Huh, strange. Let me just close Discord and reopen it. Okay. Go back to the port stage. Speak on stage. Share your screen. Yeah, so unfortunately we didn't get the previous session out too early. For those of you who weren't able to see it, I hope that the online content was hopefully somewhat sufficient. After all, what we're presenting is just a interactive format of the online content. Similar general points. We've got the online material. I think everybody will have a link. If they don't, you can ask in the chat and then we'll drop it for you. Please do stop me at any time if there's any kind of issues. If my screen goes off again, let me know. If it does, I might just move back downstairs where I did things previously and didn't have any issues. Because the internet is occasionally choppy here, but we'll see how it goes. I just want to quickly recap and go over what we did last session. Again, you just kind of see these ideas again and again, and you'll get more and more used to them. And we built things up. Like I said, we're kind of building up a pyramid, and you need to have the lower levels in order to get to the higher levels as well. So we started off with modular arithmetic, wherein we have a relatively straightforward rule, something like 5 equals 0, and that we have this clock arithmetic. You go 1, 2, 3, 4. Instead of going to 5, you go back to 0. And you can set that to whatever, 11 or 200. And in general, we've set it to like a very, very large prime number. We can use that set and setting to build a group that takes the set, gives it a binary operation, an operation that takes in 2 things, like addition or multiplication. And we also have an identity element, which is dependent on the binary operation. So in addition, the identity element has to, like, when you add that number, you have to do nothing to it. So that's add 0. And with multiplication, it would be multiplying by 1. We then smush 2 groups together to get a field, because we had the set. And instead of having 1 operation, we'd have 2. And instead of having 1 identity element, we would have 2. So just growing this up. We then had polynomials over x. We introduced polynomials in the first session as well, but we specified. I'm sorry, that's my mic here. It's off. We specified polynomials to be powers of x. We stick with 1 variable, just x. We don't need to have an x and a y and a z, for example. And all the coefficients, all the things in front of the powers of x, if we have 4x, the coefficient is 4. We kind of restrict those to being in a field, for example, F11 or FP. We then built up to this final lemma, or this idea, the Schwartz-Zippel lemma, and it says that if you have 2 polynomials and they're the same degree, and you evaluate them at a random number from a very large field, then if their evaluations are the same, with overwhelming likelihood, the polynomials are the same. We kind of sketched out a bit of a proof for that last session. And that will come into play a bit later to argue that a computation has been done correctly. Okay, so we're going to take these ideas in the in this session. In the first half, we're going to introduce one more thing called elliptic curves, and this contains fields and groups, and we're going to be using polynomials as well. We then have something called DLOG, which is like really important security assumption, and there's a particularly interesting relationship to wallets, in particular your public key, and we're going to understand that a lot better and why that security works as it does. And then in the second half, we're going to go into polynomial commitment schemes, which is, I've said before that a lot of what happens in SNARKs is to do with polynomials and us manipulating them. And a lot of the way we manipulate them is related to a polynomial commitment scheme. Okay. So I hope you're ready. Right, what I just said. Oh, okay, no. So many SNARKs do what they do over elliptic curves. In particular, most non-quantum secure SNARKs, so SNARKs that aren't resistant to quantum computers, they will generally speaking use elliptic curves. And the reason they do is that it's kind of a more efficient place to work in. Okay, Mesh can't see the slides. Can other people see the slides, or is that going to be a general issue? If it is, I will just quickly move downstairs. So it will be frustrating. Okay. Okay. If it's one person, then I think maybe to continue. So most non-quantum secure SNARKs will use elliptic curves because they're just a very efficient place to do to have our security in, and we're going to touch on that a bit later. Maybe restart Discord. I think I can restart Discord, but if it happens again, then I will run down. Oh, well. Sorry, Gijong. Okay, almost there. Oops. Okay. Sorry, I jumped the gun there a little bit. So let's dig into the elliptic curves. Elliptic curves, again, they're just a curve that we can draw on some axes, and this is the basic equation. We have y squared equals x cubed plus ax plus b. I'm just gonna go to sketch. So elliptic curves, we got y squared equals x cubed plus ax plus b. And here, a and b are just any kind of normal numbers. So, a could be 3, or it could be -4, or it could be 5.1, or it could be 271,364. Same as b. They're just kind of normal numbers. So it's actually a fairly straightforward equation. As far as mathematical equations go, it's not particularly large or scary. And the only two things we vary are A and B. And if we sketch them out on some axes, they also look fairly non-complicated. They'll either just kind of, let me do a different color here. They'll either look sort of just like this, and they'll go up to infinity that way, and down to infinity that way. Or they'll look the same, except they'll have a sort of egg or bulge just to the left of the axes. So they're not particularly scary looking curves. One thing to note, it's not abundantly clear from my sketch, but these are symmetric. So if this is 4 and this is the y value, then when we go down, we go across here, this is going to be -4. basically, if we have, the top half, if we just mirror and reflect it onto the bottom half, we will get out the bottom half. Okay, so they have symmetry about the x-axis, and that's because of the definition of the equation. This y squared, what this implies is that if y satisfies the equation, then minus y also does, because minus y squared equals y squared, because the negatives cancel out. Okay, so we have a symmetry in this curve. Yeah, here's a couple more images. They're also online. You can have a kind of bulge coming out to the left, and it may or may not be connected to the main curve. You can also have the situation where it sort of like touches it. Oops. You can have the situation where, well, this is a very bad sketch. It's sort of, the bubble just kind of touches it like that. But it doesn't matter too much. There's just a bulge and a line, and it's stretching off to infinity and stretching off to infinity. And so to the left here, all the way to kind of negative infinity, there's no curve there because none of the x values there have can satisfy the equation. But all the way to the right to infinity, you can have values that satisfy the equation. We can do something particularly interesting on elliptic curves. I did pre-sketch a curve here. So here we're going to be doing, oops, elliptic curve addition. So here I've got another sketch of one of these curves that I spoke about. And we've got 2 points. We've got P and we've got Q. We can add these points together. And this isn't going to be normal addition. We're not going to take the coordinates and add them together. We're going to kind of define a new binary operation, a way to take in two things and spit out something else. But it's not going to look like anything we're kind of used to in maths. So the way we define this is we'll get our 2 points and we'll draw a line through them. And we'll just extend that line until it crosses the curve again here. We're mathematically guaranteed to cross the line of the equation at a third point if we drew it through 2 points. There's mathematical reasons for that, and they don't particularly matter to us right now. We just can accept as a black box that there is some proof that shows that we will always intersect at a third point. And then what we do is we just reflect across the x-axis till we get here. Oops. And then we'll call this point P plus Q. Okay? So that's all we need to do is draw the line through and then find the intersection and then reflect again. Okay, so even though it's a kind of strange idea that we can build a new binary operation, this one's quite visual. It's kind of quite nice to do. To calculate it by hand, the coordinates is a lot more annoying, but it's not too complicated. But visually, it's quite nice and relatively straightforward. Just gonna copy this and can use it afterwards. Oh, wow, fantastic. Let's try that again. Copy. Okay. going to, okay. Let's explore that a bit more. Because I'm mentioning a binary operation, you're probably thinking back to groups, because this is where that terminology came in. And you're going to wonder, is there a group here somewhere? And there will be. And in order to get there, I want to demonstrate a couple more things about what we have here. Let's paste this in. Oops. Okay, so let's rub out some of this as well. So firstly, what else, if we have a binary operation and we're looking for a group, what else, what might we be looking for? What else is kind of important? Anybody remember? We're gonna need a set, yeah. Yeah, we're gonna come to the set, but what's the other thing that we wanted? We're gonna need an inverse as well. We'll get to that after, but before we get to an inverse. There were three things we needed in a group. In a group, everything has to have an inverse, but that was like not one of the three objects we need in there. Yeah, we need the identity element. So remember that for addition, if we want to, we need to be able to add something and it should be like do nothing to it. So that 3 plus something and you'll get out 3. And of course, the number that satisfies that for addition is 0. So for addition, 0 was the identity element. For multiplication, it's 1. But if this is our binary operation where we draw lines between curve points, then this gets a bit weirder. What's identity here? And we can think through it a little bit. We remember that the last step in that addition that we did is that we actually reflected across the x-axis. So if we want to end here at P, well, the step before that is to reflect across the x-axis. So here. So somehow we need to draw a line through P and somewhere else and end up in the reflection of P in the x-axis. And if you think about this, the only way you can achieve that is if we just have a vertical line, right? We'll have a vertical line because that's the only way to intersect the curve in the reflection down here. But if we've got to draw lines between curve points, is there a curve point kind of directly above P? Well, if this just kind of, if the curve is going up this way to infinity, we would say no, there's not a point above here that we can just draw a line through. And there's not. But we can just add one. We can just, in a sense, we can have our coordinates like this that stretch off to infinity and just say there's kind of a circle around it that is infinity. And we can add a point here at infinity, but infinity to the north at the top. So it's a bit strange. You can just say there's a point at infinity. And of course, because infinity is all directions, you can go in any direction to get to infinity. But we're talking about when you go just up, there's like a north star, a northern infinity. And if we just accept that that's a possibility, we can then draw a point from that north star. We can just imagine a point above P and draw vertically down through it. Because if we do, we'll intersect here where we want it to intersect and then reflect back over to get to P. Okay, so a little strange. And we call this point at infinity O, kind of like a 0. We can do the same thing with Q. If we've got Q here, and there's a point at northern infinity. I'm just drawing it here because it makes it a bit visually nicer. Then we can get a vertical line through it, intersect here, and then reflect back over and get out Q. Right. So there's a point at infinity here. The important thing to think about with the point at infinity, it just lets us draw vertical lines. And if we can draw vertical lines, because these curves are symmetric, we can turn out to be able to get back the number we started with, or the curve point we started with. So now we have an identity element. So, and like people asked last session, we're starting to find an example of a group that's not just doesn't just contain normal numbers. But you also said when I was asking this question, what else might we be looking for? We're going to look for a set, and we're going to get to that in a couple of slides. But for the inverse, we have a similar kind of thinking problem. We're going to let's just put this up. We're going to need to find an element that when we conduct this addition, we should be getting back the identity element, because that was the oops. Because remember, like we want originally in the normal groups and normal numbers, we want 3 plus x to equal, because it's addition, it should equal the additive identity element, which is 0. So x would equal -3. And in here, we're going to want p plus x, whatever it is, and we want to get out the identity element, which is this big O. So now if we try and think through that again a little bit about this. Okay, get that. Now we want to find something. Thinking backwards again, we kind of want to end at a point that such that when we reflect across the x-axis, we end up with the point at infinity. And that's a little strange. Kind of unsure how that should work. We can sort of go in any direction to infinity, but we also want to make sure that this will be consistent with addition and how we expected it to behave. So someone's asking, is the identity element unique in the way we just defined it? Like it is a unique element. There's not lots of separate here, 2 separate points to kind of represent the point at infinity, but that was just, it makes it look a bit prettier. We can imagine it just being northern infinity, and wherever we get to it, we can only get to it. It's actually about the gradient, and we can only get to it if we go like perfectly straight up. You know, we can't deviate a little bit sideways because then we won't get to the same point. We just want to do the vertical up. So it is a single point. There's not multiple copies of it. And here, if we want to get to that point that goes perfectly straight up, the only way we should really be able to do that is by going, a line vertically through, which brings us back to this opposite point again. And we can kind of maybe guess, maybe this should just be the inverse element. We call this minus p. Because what happens if we do, then if we draw a line through these two, it will just go up to infinity and also sort of go down to infinity. But if we go up to infinity, we should hit the point at infinity. And then maybe we have to reflect across the x-axis, which sort of takes us to infinity going downwards. And it sort of does. But here, when you're getting started, it's best just to kind of accept that it's, if we go vertical, we're going to hit the point at infinity, and we can take that to be the result, because we're more interested in the angle. Okay, so this is our inverse element. Okay, so what happens now if we just check, does this kind of obey our normal expectations about how addition works? Let's find out. So we have a couple interesting points here. We've got, oops, we've got p plus q over here, right? And we also know that here, well, what we're expecting now should be minus p. So what happens if we add minus p to p plus q? So do p plus q plus minus p. I mean, our expectation by writing out should be that we just kind of get out q. So let's see what happens. If we draw a line between these two, and then, you know, giving some leeway for my sketching quality, we get out q. Right, so that's actually what we were kind of expecting, natively to happen with our operation. And if we do this, it turns out to be quite logically consistent. So we've got our binary operation, we've got our identity element, we've got our notion of an inverse element, something that undoes it. The last thing we have to clarify is actually specifically what set are we interested in? Because we're not going to be working here on this infinite plane when we actually do stuff. Okay. Bringing in more of these ideas, we're going to work with something called an elliptic curve over a finite field. So rather than work on the infinite plane, we're just interested in finite field. So I've drawn a little sketch here. Here we're working over F11, and in our y-axis, we go from 0 to 11, and in our x-axis, we go from 0 to 11. Okay, and because this is a field, because it's a field, and we have like the modular arithmetic work. In F11, we have that 11 is congruent to 0 on 11. So these dashed lines at the top, this dashed line at the top is actually in the same position as at the bottom. It's kind of like if you get a bit of paper and fold it together and have the two lines touch. Those two lines are actually the same line as far as we're concerned. And the same is true on this right side with the left side, the left axis. Okay, so we can connect the paper up one side, and for the other two sides, we sort of have to connect it again. If you can't do it with raw paper, we're going to do it with one side, but it helps you visualize it a little bit. Now, if we take our elliptic curve equation, let's just say it's y squared equals x cubed plus x plus 4. I don't know exactly what it actually looks like, but let's say it looks like this curve we were just working with. Then if we try and draw in, because here we're sort of working with this quadrant, this portion here, right? So if we try and draw in that line, do the same color for purple, then this line kind of goes like that, sort of through the middle. Then we can sort of draw in this line like that. Okay. But because of this modular arithmetic group, because we have the 11 equals 0, if this point here is the same as this, because we can take away 11 and get between them, we can repeat that process, and it turns out that this point here is also the same as these two, and also going up. That's modular arithmetic for us. So this bottom quadrant can also sort of be mapped over to there. which means that this line is also in our space. Okay? And then we end up mapping every single infinite quadrant like this into this single space, right? So we've got taking this infinite curve and mapping it into this finite area. But this area, this 11 by 11, this is not infinite. You know that, it goes to 11 only, but even there, it's discrete. So if we're to zoom in here, and let's say that this point is 1, 1, then we have an infinite number of points in between here. Right, we've got 0.1 and 0.01 and 0.001 and 0.0001, and that just goes on to infinity. But none of those points are actually in our finite field because they're not whole numbers. And so even though in this area there are an infinite number of points, in this 1 by 1 square, we only have a single point. This one there. Okay. So when we draw over these lines from the curve, they will only actually be in this space if they happen to go through one of these integer coordinates. Let's just say this is 4, 10. Right, so of this whole curve, the only part that's in the curve is that bit, and the rest just gets rubbed out, and this vanishes too. And what happens is this infinite curve turns into a finite number of points here. Because if this is f11, then we have 11 times 11, which is 121. There's only 121 points in this actual graph. It's not continuous. We only have 1, 1, and 1, 2, and 1, 3, and 0, 1, and 0, 2, etc. So now the elliptic curve, I did pre-draw it, all these yellow dots are all that's left of our elliptic curve. And here there's 2, 4, 6, 8, 10, 11 points in our elliptic curve over finite field. This now looks kind of scarier, right? Originally, our original curve drawing was actually quite straightforward. You just have a bendy line that goes up to infinity and down to infinity, and we have a little egg sometimes. But then we end up in the finite field with just some points weirdly spaced about. You can see that they're still symmetric about this line. Okay, so there's still something there that's familiar, but it looks very, very different. And that's actually quite valuable to us, important, because it's very hard to connect the points to each other, and that kind of adds to some of our security, which we're going to explore soon. So elliptic curves. Oh, sorry, and specifically, this is the set that we now want to work with. All these 11 points here is going to be the set that we work with in our elliptic curves over a finite field. And going back to the idea of a group, it turns out that if we conduct the same addition logic we had, where we'll take 2 points and draw a line through them, like this point and this point. If we draw a line through them, we're mathematically guaranteed for the same thing. At some point, this line will intersect the curve at a third place. And here we can kind of go to this point, and then we'll go back up here, because again, that's because of modular arithmetic, that's the same. And then we continue with the same gradient, and we seem to hit it here. And then we can sketch over to here. So if this is P and this is Q, it adds to P plus Q here. So now we have all the things we wanted. We've got a set, and a finite set is what we're particularly interested in. We've got a binary operation, this weird curve addition that we can just draw lines between 2 points and then reflect at the other intersection. We've got the inverse element, P, minus p because of the symmetry. And we still also have this point at infinity. You know, we can draw vertical lines. And that's part we just kind of accept to be true. It's a bit, for a lot of these tools in cryptography, especially in the beginning, it's much better just to kind of accept some things as a black box that we don't know why, but we know how to use it. Again, it's kind of like Wi-Fi. Like, I don't know what Wi-Fi actually does. I know that it connects me to the internet. I don't know how. I don't know what protocols it uses or how it splits up data into packets. But I know what I can do with it. I can connect to the internet wirelessly. And that's sort of the understanding you should be going for here. We know that there's this point at infinity that allows us to draw vertical lines. Doesn't matter why it's there, we can draw vertical lines. And we're symmetric here about the x-axis or the middle. Right. That's elliptic curves over finite fields. And then you can see that addition works as well. So there are like little GIFs of this in the online content. And we've covered all the aspect of groups. We've got the identity element and the inverse. So then just before the break, we can go over this discrete logarithm problem that I just told you about. And this is actually going to be very interesting and relate to our crypto wallets. Discrete log problem. Yeah, so it's actually discrete logarithm problem. Let's just do a problem. And this is where we'll have the same setup with the finite fields. And we're going to have a bunch of points. I'm trying to draw more here just to make it a bit bigger. Okay, so we have this weird elliptic curve. And if we define this point here to be G, and G stands for generator, we're going to use, G is going to be the standard kind of name for a lot of points. If we add, we can add G to itself and get out various different points. So here, if we have, let me write this out here. If we take n lots of G and we get out P, okay, so G added to itself many times. So for example, if we add G to itself, the first one might be here and then get reflected here. So that would be 2G. And then we draw, oops, to get to 3G, we're going to draw a line between G and 2G. And then somewhere this is going to, intersect. Let's just say it's here. We have 3G, and we can repeat this process and get up to some number. We can call it n, or for a concrete example, let's just say it's 11. No, we always use 11. Let's just say it's 9G equals P. Here's the statement of the problem. If you are given G and P, can you work out N? Okay? If you're given G and you're given P, can you work out what N is? So if I give you specifically here 9G, which is P, and I give you G, can you then figure out that G was added to itself 9 times? All right, so that's the statement of the problem. And then we have something called the DLOG assumption. And the assumption is that you can't, that it's hard. The DLOG assumption is that DLOG is hard. And what we mean by hard is which means that there is no simpler way to solve this problem than brute force. So if you want to solve this problem, the DLOG problem, in this example here, the only way to do it is just brute force. You'll check G, you'll check 2G, you'll check 3G, 4G, 5G, 6G, and you'll just keep going until you find that 9G matches P. So the assumption is that there's no quicker way to do it. You just have to brute force it. And then this means is if n, that's something we know to, if n is in FP for a finite field with P elements for some really large prime number P, then you can't work out, you can't solve DLOG, you can't work out n. Okay, like theoretically you can just keep running computers, but when we make P be large enough, it will take the world's best supercomputers millions or billions of years to brute force one of these. Okay, and that's like a lot of where our security comes from when we do elliptic curve cryptography. And particularly interesting is I said it's an assumption. Like it's not a theory. Most stuff in maths we're certain. We know for 100% we have a mathematical proof that shows us something is true. This is one of the unique cases where we don't have a proof, and it's nothing to be worried about. Basically every mathematician believes that it's hard because for elliptic curve cryptography, people have been trying for hundreds of years and they've made no progress whatsoever. You can be smarter about how you conduct the brute force, but there's no way to properly directly solve it. And this is kind of related to some other big problem in math, but it's kind of easy to show that you can do something because you can just do it. But in order to prove that you can't do something is very, very tough. There's an interesting example with a ruler and compass, and that if you, let's just draw it here. If you have this and you have this angle, can you perfectly split this in two? And the proof is nice. Remember, we got compass. So you put the compass here and draw a circle around that point. This is a very bad drawing. And you could put it the other side and draw a circle around that point. And then when you get this intersection, apologies for the very poor drawing, the intersection will perfectly split this in half if you do it correctly with a compass. And that was proved thousands of years ago. They knew that. I think that might have been Euclid's Elements. They showed that you can perfectly cut this into two. But then it was asked, can you cut it into three pieces? Into three pieces. So a line there and a line there with a compass and ruler. And they couldn't do it. And they couldn't prove that they couldn't do it either. And it seems to have taken around 2,000 years to prove that that's actually impossible. Because to do it, to show that it's possible, you just can find a way to do it, and there's often more than one way. But to show that it's not possible requires a lot more understanding. And it's actually group theory that allowed a proof of this to be made, that given the operations you can do with a compass and ruler, that it's impossible to split it into three. So even though this is an assumption, nobody is worried about it. And with relation to crypto wallets, this is your secret key, public key pair. Your secret key is some number in a large field. And your public key, does it equal secret key multiplied by G? Well, G is a curve point, so it's got two coordinates. It's got, this let's do this here. It's SK G. It's got its X coordinate, its Y coordinate. But public key is like the same, basically the same length as the secret key. So it's not equal to the secret key of G, but it is equal to the X coordinate of SK multiplied by G. Right, that's actually what your secret key is a number in this prime field. And then that's why you can work out your public key from your secret key, because you can just add G together to itself again and again and again until you get SKG, right? And then we have signature schemes and other things that allow us to prove that we own the secret key, right? And again, people can't work out your secret key because we assume that they can't. But if it ever happens, things will change quickly. It seems to be very, very safe. And this is also this DLOG problem. This is why elliptic curve cryptography is not safe against quantum computers, because we know as a fact that there is a quantum algorithm, Shor's algorithm, that can break DLOG assumption, that it can take, for example, your secret key G, your public key, and work out the secret key. Okay. But so now you're starting to get to the point where you can understand more of the cryptography used in general in the crypto space. There's not much more complex objects beyond this. There are some more complex tools like hash maps and even hashing itself. But you're starting to get a very good basis of everything around. I think is that. Just for anybody who's done kind of cryptography before, if you know of RSA, which is how a lot of online security was maintained in the past, it's similarly based on an assumption that if you multiply two large prime numbers together, we can't figure out how to factorize them. That was also an assumption. And this replaces that, because it turns out you can have the same security for a smaller number, which allows you to have shorter keys and things like that. But if you don't know that, don't worry. That's just for people who already have some awareness of it. And we can take a pause here and then come back in 5 or 7 minutes for the second half, where we're going to see a kind of more complex tool to work with polynomials. We got a question from Fran. To get your public key, you got to enter G and SK. How do we get random SK? Yeah, I don't actually know what protocols they use for this to generate the secret keys. There's many ways you can use sort of what's happening in your computer to derive some randomness, and all these methods seem to be like safe enough. Some mathematicians complain that it's not like true random. It's not perfectly random, but it's very plenty for our purposes. Like I know there's one company that they use kind of lava lamps. If you know what lava lamps are, they're kind of like the liquid that moves around inside them, and they just take an image of them and somehow use their random movements, because we can't guess how they're going to move, to make random numbers. But I'm pretty sure it should just be something going on in your computer that has some randomness. Like if you code, you can get random number generators, and lots of them are based off of just what's going on in your computer. Alternatively, actually, that's not entirely true, because I guess some of them do use a different technique, because you also, for your secret key, lots of them are not, they are a string, but instead you might just have 12 or 24 numbers, not numbers, sorry, words, like tree, jump, flop, whatever those words are. And instead of calculating a secret key directly, I guess what they have, I guess they got a sort of dictionary. let's just do this lowercase. Allies, jump, whatever all these words are, 0, and then it will take 24 from here at random. So you want to calculate random numbers to get out these words. And then what you do is you're going to do a hash function. And a hash function is a kind of, we assume them to be random functions. They kind of take in something and their output is random. And a way you can think about the method we think about for hash functions is that it should sort of be the same as if you, for every new input, let's say the input is, allies, and then the other 23 words, that to figure out the output, it should be equivalent to just making up a random output, and then that output should be tied to that input. So that each new input will have a completely random output, but that if you put in the same input, you should get out what you got previously. And that's why you can also recover your account, your secret key, your public key from that list of words. Because the list of words, they just put it through a hash function and get out the number that they had before. And one of the reasons why they want to use words, kind of 24 words, it's a bit easier to look after. If you've got a long string, 0x358, whatever, if there's any damage or some bad writing or things like that, to figure out what the whole number was, it's very hard to figure out what changes should be made. But if you've got like jump, and it's a bit skewed, you can probably tell that it's jump. It's like a lot easier. I don't know the size of this list of words. I'm pretty sure it's massive, because it's sort of like a dictionary attack. But the fact that you put 24 of them together, that makes it unbrute forceable. If it's going to be, if this list is 2 to the 10, and then you do it to 24, like 2 to the 224, it becomes a very huge number very quickly. That's why some of them use like 12 words. I think maybe MetaMask does, and that's like a lot less secure. If you have a cold wallet, sometimes they'll have like separate accounts inside them where you'll enter a passphrase. And if you do, that's actually what it's doing here. It knows your 24 words, and your passphrase is kind of a 25th word that's added. Passphrase. And in that way, you can get a different like account on the same cold wallet. Yeah, Ken. I mean, because the words are, short, it sort of feels like you can. But if you check the probability, you put 24 of them in a string together, that's suddenly like a very, very huge probability space to look through. Again, because if it wasn't, we would just double the number of words, and if it still wasn't sufficient, we'd double it again. And it turns out that 24 is actually sufficient for most of us. I mean, basically everybody. Like 12 is you should be more cautious about. Okay, just another 30 seconds or so, little break. Okay, I think we can get on with the second half. And here we're no longer going to be introducing new mathematical objects from here on out. We've built all of those. We're now going to look at a kind of more complex system through which to work with them. And then next session, we'll see briefly how to use that system to kind of do PLONK in a bit more detail. And then we'll explore just some other proof systems at a very high level. So first thing we got to cover is that we can sort of evaluate polynomials not at normal numbers, but at curve points instead. There's a little bit not entirely true, but that's the easiest way to think about it. Yeah. Evaluating polynomials at EC points. Let's take a polynomial, fairly straightforward. Let's do f of x equals 3x squared plus 4x plus 2. Now, we've seen before, and you probably did lots at school, you can evaluate this at a normal number. If we do f of 2, we got 3 times 2 squared plus 4 times 2 plus 2, which is 6 times 3, which is 18. Sorry, that's 4 times 3, which is 12, plus 8 plus 2, which just gives us 22. All right, so fairly straightforward, we've seen before. But we can also evaluate it, if we've got an elliptic curve and all its points, if for our actual elliptic curves, there's billions, like huge 2 to the 256 points on there. And this one here is G, our generator, because if we add G to itself non-stop, we'll actually go through every point in the curve before getting back to G. So that's why we call it a generator. It kind of generates the whole set. If we're to instead do f of, we still kind of write f of 2, and then instead we just, let me do this in a different color. We append G to everything, because f of 2, 3 times 2 squared G plus 4 times 2G plus 2G equals, well, it's 22 before, so it's going to be 22G this time around. So it looks the same, except that we just chuck a G on at the end. And the reason why we don't put in like f of 2G, you might, if you had some time to think about it, you've hopefully go down this logic route, but an elliptic curve it's a group. Right? We can make a group from it, and it's a group, but not a field. So what does that mean? It means that we only have one binary operation, but so it's either addition or multiplication. So if we tried to do this, we'd get 3 times 2g squared plus, and here you'll see that we've got to do 2g squared. That's 2g multiplied by 2g. But then we need to add afterwards. So we'll be trying to do multiplication and addition. So we're not exactly putting a curve point in, because, yeah, it would defy the kind of rules we made. But there's another way we can do it so that we don't put in 2g, we put in 2, and there's kind of a g there for us. And you might be noticing now and thinking about, well, if you get out 22g, well, we don't know it's 22g. Like if you give it to me, I don't know that it's 22g. I just know that it's some curve point, p. And you can sort of see that we're hiding a number in there. But the point here is just that you can evaluate an elliptic curve sort of at an evaluate a polynomial at an elliptic curve point. And then we're about to connect this in because if you remember, I'm going to sketch it out, but we made polynomials during our proof system. So I think next slide, I'm just going to do a sketch of where those polynomials are. Oh, okay. So before that, we want to talk about something called a point of unknown order. And again, this is because of the DLOG assumption. It can be in lots of places. If we're given a point P, and we know it's NG, we don't know what N is. And this allows us to hide a number there. But this is also sort of a form of randomness, which I'm going to show. Yeah, I mean, we've seen this. If I give you P, it's 22G, but you don't know it's 22. It's hidden. So if we can find a way, what we want to do is find a way to make something like that where nobody is going to know that it's 22 or whatever number it is. Yes, this is what you might see this name around. This is called a trusted setup ceremony, or a powers of tau ceremony is another name for it. What we want to do is we want to get out T, which equals, call it SG, where nobody knows S. We want everybody to know T, we want everyone to know G, we don't want anybody to know S. In the online content, we didn't want to dig into it, so we just said, imagine somebody you just really trust does give this to you. So, for example, David Attenborough, he makes T from S, he gets an S, he multiplies it by G, gives you T, and then he just deletes S from his computer. And I trust David Attenborough. I trust that he's given me a real thing and that he doesn't know the number. In real life, in the trusted setup ceremony, it's a very effective design in that if 10 people take part, only one of them has to be honest for the number in the end to be secure. And so if it's not 10, but it's 100 or 1,000 people, need to one of them be honest. You can, if you can't trust that 1 in 1,000 people, a single person out of 1,000 is going to be honest, then I don't know if there's a basis for online communication or systems. But we don't. It's not actually just T that we want. We want more than just T. We also want T squared, which is S squared, G. We also want T cubed, which is S cubed, G. Okay, and then we're just going to go, and then we want up to some large number, like T to the N, which equals S to the N, G. Okay, so we want actually tons of these, up to some maximum number. For ZK friendly, your question, why can't we do 2G squared? Well, because that equals 2G multiplied by 2G. No, I know what 2G plus 2G is, because in our curve, we drawn it here. This is 2G here. Right, so I know I can draw a line through it, and then that's going to help me find 4G. Because we defined addition, but we didn't define multiplication. We only have one binary operation, and we said that it's addition. But then we go and say that we want to multiply an elliptic curve point by an elliptic curve point. We didn't define a multiplication, right? There's no there's no concept of multiplication here. You know, in addition, we draw a line between 2 points and it intersects somewhere else. That's how we do addition. How do we do multiplication? We don't have an equivalent. So we're not allowed to do multiplication. There's no definition of what multiplication is. But that's actually a good point to bring up something else. Notation-wise going forwards, if you're going to be looking at elliptic curve stuff, because we have only one operation, one binary operation, sometimes it's written like, here I'm saying we have g plus g, and that gives us 2g. But in a lot of places, instead of doing additive notation, we do multiplicative, where it's kind of g times g equals g squared. And sorry if that's a little confusing, but there's only one binary operation, but sometimes it's written like this and sometimes like that. So that scares you a little bit, just kind of ignore it for now. But then if you see inconsistent notation later, I'm trying to think back to this. But going back to this setup ceremony, we want to get out these powers of t. And the reason why we want these powers of t is that if you remember that we drew our circuits, this circuit here has 3 gates. In order for us to make a proof about this circuit, we're going to need t and t squared and t cubed. Okay. So what you might see here is this value n is going to represent the largest circuit we can make. So if n equals 1,000,000, our largest gate circuit can have 1,000,000 gates. This is the issue of I think this. It's not very often that this will be a problem, because I think they make 1,000,000 or 10,000,000 of these numbers. But once it's made and you only got 10,000,000, if you suddenly need a circuit that's 12,000,000 or 20,000,000 or whatever, you can't make that circuit, unfortunately. You'll have to do another trusted setup ceremony and get a larger number. You can't just have 1,000,000 and add more on top. The only way you can do that is by knowing the secret number from beforehand. So it doesn't quite work. Right, but it's kind of elliptic curve cryptography here that makes us need this trusted setup ceremony. Like, there are some proof systems out there, some of the post-quantum secure ones, they don't need this trusted setup ceremony, but PLONK does, and lots of them do. Groth 16 actually needs a setup ceremony for every single circuit you make. If you don't know what Groth 16 is, don't worry, but for those of you who do, you've got to do a setup ceremony every single circuit. I just want to re-sketch how we made our polynomial so that this next part will become a bit clearer. So this is actually just recap. How bigger can n be in a trusted setup ceremony? Are you asking like how big it can be? Because you have to decide its value and then you just work with that. So we might say, hey guys, let's make n 10,000,000, and then we run our setup ceremony, and then when it's finished, we're going to have 10,000,000 of these points. But we can't add more of them later. We can update the 10,000,000 we have and add in another 1,000 people to contribute to them, but we can't add more of them. If we want to go from 10,000,000 to 100,000,000, we've got to do an actually new setup ceremony, and it will take a long time. So recap, in previously when we made a circuit, remember here we had, oops, those are not actually connected to an addition, right? So we had this, oops, not what I meant to do, get this a little bit further away. Let's put in some numbers, 3 and 4. So this is our base circuit. This is the let's call it the starting circuit. And then again, just recapping from last time when we went over this. Then we're going to add it. Oops. We're going to add in the witness. Let's just do 2 and 2 again. 3 times 2 is 6, and 2. Sorry, that's 3 plus 2. 3 plus 2 is 5, and 2 times 4 is 8. 8 plus 5 is 13. And to Ken's question, PLONK is universal, but what universal means is that you only have to do one trusted setup ceremony, and then you can reuse the secret numbers, the points of unknown order is what we call them. We can reuse them again and again. Groth 16 is not universal, so it has to do one for each circuit it makes. Like if this is the circuit, it's got to do one for this circuit, and then it can reuse this circuit. But if you make a different circuit, you've got to do a trusted setup ceremony. And hopefully you remember here, we turn this into polynomials. Polynomials. I say we, I mean the prover. Only the prover can do this because they're the ones who know the witness. Polynomials, we're going to have, let's do a few different colors. We're going to do L of x, and this is going to be left for the left y. So this is 3, 2, and 5. Why does it change these lines sometimes? 2 and 5. So we're going to do 3 plus 2x plus 5x squared. We're going to do R of x, and that's the right wire, right wire, right wire. So that's 2 plus 4x plus 8x squared. And then we're going to do the last one. We're going to do O for output y for the output wire. So this is an output wire. This is an output wire, 5 and 8, and 13. 5 plus 8x plus 13x squared. Okay, so let's just recap. That's how we made polynomials before. And now maybe you're beginning to see how we can use some of this stuff. If we have t and t squared and t cubed, now we can commit to L of x. We can do L of t. That's going to equal 3g plus 2t plus 5t squared. Okay, well, what's that equal to? Well, we got 3g, and remember that we said that t equals sg, right? Is it s what we used? Yeah, we did s. So 3 equals 3g plus 2sg plus 5s squared g. And if we add that all up together, we're going to get 3 plus 2s plus 5s squared and then g. Okay, so that's what it evaluates to. But for me or you or whoever receives this curve point, this just equals like p. I don't know how many g's are in there. I just know that it's p. And this is our commitment. Well, commitment to L of x. Because we made it from L of x, and it kind of collapsed that information in this case from 3 points into 1 point. But if our circuit had 1,000,000 gates, then we would collapse 1,000,000 values into a single value, right? And if you give that to me, I can't go back and work out what polynomial you had. If I could, I would be able to figure out your witness, but I can't. Like, you just can't do that. And then we can go on. We can do R of t, which equals 2g plus 4t plus 8t squared. And again, that's 2g plus 4sg plus 8s squared g. And then that's 2, oops, go with that. G2 plus 4s plus 8s squared g. And then we can call that p prime just to distinguish it. And then, of course, we can do the O of t. But one really interesting thing to notice here is that L of x was evaluated at a random point. Okay? Everybody knows t, but nobody knows s. So what this is actually equal to is, sorry, not f. It's equal to L of s multiplied by g. But nobody knows s. So even though we're evaluating this polynomial at a known curve point, the polynomial itself is being evaluated at an unknown point. And a way to help you understand that is that if we're going to evaluate L at a random point, then we'll evaluate L and we'll come up with a random number, let's say 7, and then we'll evaluate it. But then when we evaluate R, we can't use 7 now. I know that it's going to be 7. I can modify my polynomial to give a certain value at 7 because I know it's going to be evaluated at 7. So then I would need kind of a different random number if we want to make it random each time. But in this scenario, we all know t, but it's still random. So we can reuse it for R, because even though we know t, we don't know s. Okay, which, is a very strange idea. And that's very helpful for a couple reasons, because then we don't have to make as many random numbers. But also in the start, in the very beginning, for the first bit of randomness we need, we already have it. If instead the prover made L of x, their first polynomial, where would they get a random number from to evaluate it at? They could use their polynomial L of x and like hash it or do something to derive a random number. But then to check that, they'd have to reveal that polynomial, and then they'd be revealing their witness, so it doesn't work. Or maybe there's some online place you can get a random number, but then that's not trustworthy. We have some issues there. But in this scenario, we got everybody together to make a random number that we all trust is random. And then once we use it, we can actually keep reusing it. Okay. So then we get out P, we get out P prime, and then we get out P prime prime as well for the third commitment, O of t. And that's the start of our polynomial commitment scheme. We've now committed to the polynomial, but we want to do something afterwards, because if the prover just commits to them, like, then what? What's the point? Let's just go return to the slides. Polynomial commitments, we're going to value it on an order. What's going to happen is that the verifier, what's the point of committing? The point of committing is that once we make the commitment, the prover can't now change the polynomials they started with, right? They can't change their starting polynomials. If they do, we're going to be able to tell. We're going to see that their commitment doesn't match the polynomial that they're now claiming that they have. In in the online material, what I say is that the prover will reveal their polynomial later to check their value, that the commitment was valid. That's not what we actually do for two reasons. The first, as you can probably tell, if you reveal the polynomial, you reveal your secret information, your witness, and it wouldn't be zero knowledge. Secondly, if you had to reveal the polynomial, and these polynomials can have 1,000,000 points, you've got to communicate 1,000,000 points to each other. So, really not ideal, very slow, and reveals the knowledge. But instead we have something called an opening proof. And the opening proof is a part of the polynomial commitment scheme. It's going to allow the verifier, or us, to check that any new value that the prover gives us, we can then see if it came from the same polynomial. So what's going to happen here? We've got the three commitments. The prover knows, of course, their polynomial. What's going to happen is the verifier is going to create a random, another. Well, I guess it's not another because they've not created one before, but they create another random number, alpha. Okay, let's not use alpha. Let's just do A. Or R, small r. Okay. And request L of R and R of R. Okay, bit of abusive notation, but okay. And O of R. So then the prover gives Q prime, not prime, Q prime, and Q prime prime, which he's claiming that Q equals L of R, and Q prime equals R of R, and Q prime prime equals O of R. Now that the prover's giving us these new evaluations, how does the verifier know that these equalities are actually true? And that's what we're going to use in our polynomial commitment scheme. Does the verifier know the form of the polynomial or only the result? The only thing the verifier knows is the degree, the size of the polynomial, the highest power of x, because the highest power of x is the number of gates in the circuit. But aside from that, they don't know. They will actually know a couple of the values, like in this example here, you see that 3 and 4 are actually pre-known values. They were already decided. So the verifier might know the small bits, but they don't know much about the polynomial. So now the prover's given new evaluations that he's saying are from the same polynomial. And we can actually check whether they're from the same polynomial, because the prover will not just send Q and Q prime and Q prime prime. It will send a proof. This is not the zero knowledge proof. This is like an opening proof. Opening proof. And P prime and sorry, pi prime prime. And there's a way for us to check in a polynomial commitment scheme. We're going to check that we're going to put in P, which you remember was the commitment, the original commitment, Q, which is the new claim value, and pi for the proof. And this is going to do one of two things. We're either going to be happy or we're going to be sad. And if we're happy, it means it checks out. It means that P and Q are from the same polynomial. And we're going to be sad if it turns out it doesn't pass. P and Q are not from the same polynomial. It doesn't matter how this check works. All that matters is that we can do it. But this happiness is actually occasionally there'll be a passing proof that shouldn't pass. But this is actually where the Schwarz-Zippel lemma comes in. That if the prover was honest, their thing will pass, because remember that the polynomials will evaluate to the same value. But occasionally you can have two different polynomials and evaluate to the same value. So that's, we got Schwarz-Zippel going on here. In fact, the final check in PLONK is basically a ton of these checks all mushed together. You got like tons of them, but you can actually squish them all together into one. And then we check that. And that's actually why the PLONK proof comes out as probabilistic, because there's some small chance that it was fate. But why does the verifier actually like want another another evaluation from these polynomials? These polynomials are designed in such a way that we can actually predict how they're going to behave. And more specifically, we have an understanding how Q and Q prime and Q prime prime relate to each other. We have expectations about how they're going to relate to each other. You know, not if we evaluate them at random number, we don't know what we're going to get out. But we know that if we evaluate them all at the same random number, because of the way we designed these polynomials or chose them, we can have expectations about how they'll work together. Okay, so that's why the verifier wants more evaluations. So the prover is going to represent their filled-in circuit by polynomials. They then commit to them, so represent. They then commit to them, and then again, the point of the commitment is so that the prover can't change them. And then the verifier can start to kind of question or query their polynomials. So this is kind of the query / question the polynomials. And then the verifier, with these results, can kind of play around with them and see if they behave as they're expected. And that's what we're going to see in the brief overview of PLONK next session. So just to recap, polynomial commitment schemes, they take in a polynomial and they compute a commitment to the polynomial. They don't stop there though, because if you just commit to polynomials, it's sort of like, what's the point? Unless you reveal the whole polynomial later. But that's not ideal. We have much better techniques. The ones we're interested in, they allow for something called an opening proof, which is just another field element or curve point, actually. It's just a single curve point. And that can be used. So that was this little pie that I drew, the opening proof. That curve point can be used to check whether the commitment and a new evaluation from that polynomial are actually from the same polynomial. Okay. So it's quite a big complex system. There's a lot more to it in terms of the details and how it works and why it works and how you might implement it. There's a lot going on there. But a lot of what happens in elliptic curve based SNARKs is polynomials. We use discrete log for a lot of the security to make sure we can't, so that we can have random numbers and also have an identity, because the public key is protected by the DLOG assumption. And then the polynomial commitment schemes are going to allow us to, after representing a circuit in as polynomials, will then allow us to evaluate those polynomials and query, because if the circuit was filled in correctly, we know how these polynomials should behave. That's one of the crux. That's like the crux of what's going on. Because of how we chose or designed these polynomials, we know that if the circuit was filled in correctly, because the polynomials are a representation of the circuit, we know how they'll behave with respect to each other. And okay, that's the end of this session. So in the first half, we introduce another object, elliptic curves. When we show that elliptic curve, we can get a group from it where the set is the elliptic curve over a finite field. We introduce this kind of strange new binary operation that we call elliptic curve addition. And we have this identity element, which is this point at infinity that just allows us to draw vertical lines. We have the inverse elements, which are the reflection on the x-axis of points, because our curve is symmetric. And then we introduce the discrete log problem, which is a security assumption that is not quantum secure. That is how a lot of our wallets represent our identity. And then we've seen in a polynomial commitment scheme that allows us to commit to polynomials and then show that new evaluations came from the same polynomial. So there's a bit of like a whiz tour through a lot of the maths that's going on here. And for right now, it's really the best thing to do is kind of make as many of these black boxes as possible and just say, like, this does that other thing, like a functional understanding, like I mentioned about Wi-Fi or the internet, even getting water out of a tap. Like, I don't know where the water's coming from. I don't know the whole system behind it. I don't know how the internet works. Well, I kind of do a little bit, but not very well. But it doesn't matter. I don't need to know all these different protocols. I just need to know how to use it. And a lot of what you can do with these tools is use them as black boxes. If you know what's allowed and what's not allowed, that's perfectly fine. Because when we make SNARKs, because these numbers, these wire values, they're elements of a finite field. So when you're coding, if you're going to be a programmer, if you're coding, there's no such thing as an I8 or a U64 or a string. Everything is just a finite field number. All right, so there's a maximum number, and there's only certain things you can do. You can only do addition and multiplication. So if you want to represent a string, you've got to have like a more complex system in logic inside that will tell you how to represent a letter as these numbers. This isn't full. This is like we call it vanilla PLONK or very basic PLONK. There are different types of gates as well. We can have like a lookup gate that will, you can check if something's in a table, and a variety of others that give a bit more diversity. But because of this setting, it will determine in large part how you're allowed to code stuff. Another thing is that you can't really have an if condition in a circuit, because in a zero knowledge circuit, it's just a set circuit. And if you have like a, if yes and if no, and this is an and this is an or whatever it's going to be, you can't like occasionally have the left side and occasionally have the right side. You can only have both of them. So any branches that you'd have in a normal computer program, here, if you have them, your circuit is bigger, which slows it down a lot. you know, you're gonna have to evaluate both of these, even though you actually want one. So if possible, you want to avoid having a branch and try and represent it in a single thing. Okay, but that's a bit off topic. For homework, I mean, I'd recommend Anki cards for like, what is an elliptic curve, an elliptic curve group? Why can we hide numbers? Which is really important. And then how can we commit to them? And what else does a PCS, a polynomial commitment scheme, allow? So of course I'll stick around for questions, but like a big well done to everybody for getting through all that. I know it's not really very nice, and sometimes you listen and it's kind of very tough because these are dense topics, and this is really a whirlwind tour to show you as much as possible, a broad basis, but a little bit everywhere, so that you can have a basic, you can have a conversation about a lot of this stuff, and that you can enter a more advanced course and be much more productive there. So yeah, I'll stick around for questions. Ken, I have a question, maybe not directly to this, and kind of not a fundamental question, since there's something moving. Right. So if you want to think about modularity of a proof system, if going back to the image from kind of the first, you have your idea, and then you have an idealized circuit, but we can just skip that part and go straight to the circuit arithmetization. So what's allowed? We've got Plonkish arithmetization. That's the arithmetization we do here with the addition gates, the multiplications gates, or they can be something called rank 1 constraint system, which doesn't matter how it works, but it's just another option. Or there might be something called an algebraic intermediate representation. And there's some other ones out there. There's like versions of this, like relaxed R1CS or yeah, I can't remember the names of others right now. So there's some of those that you can choose from. And I say that we go from witness. With the witness, we may go to polynomials. So the way we'd represent stuff as a polynomial is kind of standard, but it doesn't just have to be a polynomial. That other systems can use different things, but they kind of want to represent stuff somehow, and then we sort of like check polynomials behave. So to do this, to check that they behave, we're sort of using our polynomial commitment scheme. It's actually something called an elliptic curve pairing that we do at the end. But this is where like a IPA might happen instead, and there's different types of things that could happen here. And even if you're going to choose, even if there is a polynomial commitment scheme, you can change which polynomial commitment scheme. There are different options. So there's these parts. You can choose stuff here. There's stuff here that can be chosen. The polynomials that we make in PLONK, you actually have a choice as to which polynomials you have. You can change the polynomials so that you can add different types of gates. I mentioned that you can do like a lookup gate and some other types of gates, like up here. So the choice of polynomials will affect the kind of gates that you can make. So you can like use Halo 2 or like use PLONK and change which polynomials the specific polynomial you want to work with here. Or you can have a bigger change and try and change the arithmetization or change the argument at the end. A lot of these changes, like this choice and this choice, these are more by like SNARK experts who are making proof systems. But this choice is like if in your ecosystem you can be like, we want this type of gate as well because of the type of computation we do, it's going to be particularly effective, and we're going to get rid of this other gate because we barely ever use it, and all it will do is slow down the system. Yeah, there was one other thing I wanted to mention, but that suddenly slipped my mind. Yeah, but oh right. So you also have a choice of like which elliptic curve to use. BLS 12381 is a popular curve. It's got 381 bits is the size, but this curve has certain properties. And in general, it's a very good curve because it's very popular. So there's a lot of like tools for it and implementations in different places. But you can change which curve you use. You don't have to use this one. I think this is the one that Ethereum uses as well. So they got another choice there. And a lot of these are really just swap in, swap out. You know, you can use a different curve if you want. And the elliptic curve was defined over FP, and you can choose FP. I mean, in BLS 12381's actually already chosen FP, but you know, that part is separate to the elliptic curve equation. Next session, we'll see like a couple other things you can choose from as well, because more properties, because you can have something called recursion as well, and some other stuff. Yeah, for a lot of cryptographers, the elliptic curve stuff is just a black box. Like some people understand and coded how elliptic curves work and how to do addition and how to do it efficiently and how to do this pairing operation at the end. But I mean, like, you don't need to dig into the details. You just need to know that if you're working in F11, that 7 plus 8 is not 15, but it's 4. Like, that's the only part you really need to know. Okay, so next session is not going to be, there's not going to be much like theory. We'll do a little bit of PLONK just to sew all this together into that large idea, but that's really quite short first half. And then we'll explore, just chat about some other systems out there. We're not intending to code a proof system together, and there's quite like a big undertaking. If you want to do it, it'll be a very, very good learning, very good way to learn. But like, I mean, a fair amount of the logic is when you break it down to the separate pieces of like how the logic works. It's very doable by yourself, ideally in groups though. But then when it comes to like, how do you write code for like how to make these circuits? Because how do you like put gates down? How do you write code for that? And then how do you connect the wires together? Is just that, I mean, that's like a lot more like logistics annoying, where like, you know, visually we can imagine we just plonk down gates, but then code wise is a bit more annoying. I mean, if you don't want it to be a generalized system, you can just have it be a very basic, ineffective way to put down gates. And then just check if it works. It'll be very cool to learn. But really, plonk by hand is like a very, very nice way to see what's going on from start to finish, similar to some of the stuff I've done here, or that SNARKs tutorial at the end of the online content. I've not done that one, but I'm pretty sure. I think it kind of goes through the theory behind it and also coding some of it in Python. So yeah, the Rust is very popular. I mean, of people who use programming languages, Rust community is like the most happy. Like we really like coding in Rust. It's really nice, but it's also you can make it very efficient. And for things like cryptography, which if you're not careful will be very slow, it's particularly appreciated and valuable to have there. But you don't have to, if you just want to do it for learning purposes, you don't have to use Rust. You can use like a Python instead, because again, it's for your understanding of like how the system works and things like that. And some of the tools, like the repositories, libraries, cargo packages in Rust, like for cryptography, they're good, but some of the APIs aren't as nice. They're a bit more restrictive by design, because then it helps prevent errors. But if you're playing around, then Python might just be a lot quicker and a lot more frustration free. My pleasure. So I'll stick around a bit longer, but if there's no questions, I'll just hop off. We had more sketches this session than the last two. Thanks, Charlie. I hope there was a successful recording. It's appreciated. To take that stress off as well.